Welcome to the solution video for the prime number challenge. Let's get started by going to File, New Project. And we'll select Console App. And we'll say this is a console UI. And this is the prime number solution. All right, and we'll put a console readline at the end. And let's jump right into creating our check for prime method. So private, static, and let's just do a bool for now, which is yes, it's prime, or no, it's not. We will modify this in a little bit, and we'll take in our number. So let's check for prime. Let's say bool is prime, or actually output, equals false. And at the very end will return false, but not yet. And actually I want to change this to true. Normally I initialize booleans to false, but I'm going to do a check here to see if we find any factors other than 1 and the number itself. So if we do, then in that case, I'm going to say, okay, that's false, and then we'll return from there. So let's say 4. So I equals 0, I is less than or equal to, and I'm going to say max here for now. I'm actually going to start this at 2. So I'm messing things up already. Let's do int max equals the number divided by 2. Okay, so I don't want to do the calculation over and over again in a for loop, so I'll do it out here. So this max right here is going to be the number. So let's say it's 10. Let's do 18. So 18 divided by 2, that means the max is 9. Now, why am I going to half of the overall number here? Well, because I'm dividing by 2. And so I divide by 2, that's the smallest number I can divide a whole number by. So therefore, if it's true, let's say, 18 divided by 2 is 9, therefore that's not a prime number, then I'd say false. Let's say it's 19. 19 divided by 2 is 9.5. Well, going on an int, that's going to get rounded down to 9. So in that case, what's 19 divided by 2? It's 9.5. Divided by 3 is smaller than that. Therefore, I don't have to worry about these numbers being prime above halfway. Okay? I know it's kind of hard to visualize, but let's do it this way. Let's write out something simpler. Let's write out 7 and 8. Okay, so 7, and then we'll write out 8. So 1, 2, 3, 4, 5, 6, 7, and of course 8. We don't need to check for 1 because we're saying that we're not going to allow, that's not one of the factors. So therefore 2 through 8. We don't need to check for 8 itself because that's not one of the factors. So now here's the things we need to check for. 2, 3, 4, 5, 6, 7 for 8. So let's run a check for 8. 8 divided by 2, yes, that works, but that's 4. Okay? So now if I moved up 1, let's pretend like that didn't match for a second. 8 divided by 3, what's that? Well, that's less than 3. It's 2 something. Notice we're going this direction. We're going back towards 2. So we're never going to find something where the result is 5, 6, or 7. Therefore, we can cut these off entirely and say we're not going to check for them. And in fact, we can cut off at the middle itself because 8 divided by 2 is 4. So therefore, we don't need to check for that either. Therefore, we can cut it in half. Let's try again with 7 just to kind of show us out. I won't put 1 or 7, so 2, 3, whoops, not M. 2, 3, 4, 5, and 6. So if we check for 2, what's that? 7 divided by 2 is 3.5. So therefore, we'll never hit 4, which is the middle. So therefore, we can actually cut off all of these and only check these 2. Okay, so that's what we're doing here. We're cutting in half. There is a way to check for just the using square root to find even smaller set. But really, we're just doing simple math here. We're not going to try and get into learning some more advanced ways of thinking. It's hard to visualize. And I want you to be able to visualize what's happening here. So I'm going to say if the number modulus I equals 0. Now, the modulus, what it does is, and if you watched a previous challenge, I did use this as well, but the modulus, what it does is it checks for the remainder. So if I had the number 9 and I divide it by 4, so 4 goes into 9 twice, but it's left over 1. And so that's what the modulus finds, is return 1 then. There's 1 left over. So if there's nothing left over, what does that mean? Well, it means that we've successfully fully divided it. So 8 divided by 2, it goes in 4 times, the remainder is 0. Okay, so therefore that determines that 8 is not a prime number. So if we find that we have return of 0, then we're going to say that output equals false, meaning we have determined that it's not a prime number. So at the end of this, return output. Now we could at this point also break, which means it's not going to check anymore. So if the first one it finds, it's going to stop. That makes it a little bit more efficient. So let's call it up here. What I'm going to do is I'm actually going to create a little bit more code than I normally would in a test project like this, just because I want to make my life a little simpler. I'm going to have it create a loop. So string continue looping equals empty string. So do while continue looping to lower equals yes. Okay, so there's my do loop. It's going to execute once, but then it's going to check to see if continue looping has been set to yes, and if so, go back to the beginning and try it again. That allows me to do multiple checks for prime numbers. So console.write, what number do you want to check for prime? Oops. There we go. And then we're going to say string num to check text equals console.readline. Okay, so there's our number to check, but it's in the form of a string. Now, this is test code. This is not for production. This is just to test out our prime number. It's not for us to be, fully compliant with everything we're worrying about, like error handling and logging and, applying solid and all the rest. So what that means I can do is I'm going to say int num to check. Notice it's just num to check, not num to check or text equals int.parse num to check text. So I'm going to parse that as an integer. And why did I preface all this with saying it's test code? Well, if you pass in a regular string like TEST, it's going to crash the application. It's assuming that you've passed in an actual integer. And if you have, it's going to parse it. Now, what we'll do is we'll say bool result equals check for prime on num to check. And then if, let's actually change this from result to is. That says, do you want to continue? And put in parentheses, yes/no. And then say continue looping equals console.readline. And that's where we update this value. Always make sure you update that value. Otherwise, you'll never exit the loop. You'll have a continuous loop. Or in this case, we won't because I started off at an empty string intentionally so we could not get into that continuous loop mechanism. All right, let's try this out as is. So let's check for some simple numbers. Let's start off with 17, which I know is prime. 17 is prime. Yes. Let's check for 8. 8 is a composite number. Yes, and let's check for another big one. I'm going to do this randomly. That's a composite number. Okay, makes sense because it actually ends in 6. Let's end another one in 7. That's a composite number as well. Okay, so actually in my testing, I pulled out a couple of very large prime numbers by accident. I actually thought my algorithm was broken. And it wasn't. I was just creating prime numbers. Okay, so let's hit no. And we can get out of this. Actually, we don't need this console read line anymore because we stop right there. So we can get rid of that. All right. Now we've completed the goal of the challenge. We are not reliant in here on console read line or write line, which means that we could actually use this in ASP.NET MVC or in WinForms, WPF, or anything else because it just returns a true or false is the number prime. It does not have anything to do with which user interface it works in. Whenever possible, create your methods like this. We're not dependent on a user interface. That allows you then to take those methods and put them in a library and reuse them in other places. Okay? But now what we're going to do is move on to the bonus challenge. The bonus challenge says we want all the factors for a number besides one itself. We want all the prime factors for a number. And we want all to be unique. And then we also want the largest prime factor. Now, the way I'm going to tackle this is I'm going to create a list. So I'm going to have a list of items where it says, okay, here's a number and is it prime or not? So this list, maybe another factor is 4. Of course, that's not prime, but may I have 7, and that is prime. So I'm going to create this list of these pairings. Now I could create a struct to hold this and just have 2 different variables in it, one being an integer and one being a Boolean, whether or not it is prime or not. And actually I'm going to create a nullable Boolean because I want the third state to be null, meaning we don't know. But I think it's easier to do something like this. Dictionary of type int nullable Boolean. Like so. And of course, we have to get rid of our Boolean for our output. Okay, so that's what this is going to hold, is a nullable Boolean. Now, if you're not familiar with nullables, they put a question now. Then afterwards, I'm going to say if output dot count is greater than 0. So if you found some factors, then I'm going to do a for each. So for each item in output, let's call this factor. I'm going to do a check for prime. And I'm going to check that factor. So how do I do that? Well, actually, it's really simple. I already have the method written. It's called check for prime. So if check for prime on factor dot key, that's the number we've added. Check for prime on this. If its count is equal to 0, then I'm going to say that factor dot value equals true. Whoops, can't do it that way. No problem. I want to modify the value for the given key. So all I'm going to say is output at factor.key equals true. Else, and this is false. Okay, I'll explain this in a minute what I'm doing. Not factor, false. Okay, so I'm doing a check where for each factor I find, so let's just write it out here. Let's do 16. So 16, the factors are 2, I'm doing this by memory, 4, and 8. All right, so I'm going to have 3 entries in my output list, 2, 4, and 8. And I'm going to call a check for prime. Let's start on the first one on 2. and how many values will I get back for its own factors? In this case, none, which means if I get none back, that's a prime. Therefore, I set that value to be prime. If I do get values back, so for example, 4, I'll get back just 2, because that's one of the factors of 4. 2 times 2 is 4. Therefore, I'll get 1 back. Therefore, it's not a prime. Therefore, I set the value to false. I don't care about the actual values coming back. I just need to know, are there values coming back? That's all I care about. Remember, I'm only counting on unique values. So therefore, I only want the prime numbers to be marked. So I'm going to say true for those prime numbers, and for everything else, if it has values coming back, I don't care. I just know they're coming back. Therefore, it's not prime. Therefore, I set it to false. Then I return my output. Up here, things are a little bit different. I'm going to grab this dictionary right here and say factors. And we're going to say if factors.count equals 0, then it's a prime number. Else, but we can't just do it's a composite number, which we're going to do. We also will have to add those two different things we talked about. We need to add how many factors does it have, and then list out all the unique prime factors, and then also grab the largest prime factor. So let's start off with the console write line that says there are factors.count factors in num2check. So that's our total count of the factors that go into that number. Now what we need to do is we need to list out how many prime factors there are and then what the largest prime factor is. So let's do the largest prime factor first. Now this is where it gets a little bit tricky because we're working with a dictionary, not a normal list or an IEnumerable, because dictionaries are a bit different. And we wanted to use a dictionary because I wanted to have this int be unique. See, if we somehow put a duplicate in here, it would actually say, nope, can't do that. So that's a little bit of protection for us, but it does cause us some problems. Now, don't worry, we can solve these problems. So we have back our factors, which is a dictionary of int, bool, nullable bool. So what we can do is create a list now of all of our prime factors. So let's just say a IEnumerable of type int, or call it prime factors, equals, and I'm just going to say from x in factors, or let's call it factor. So from factor in factors, where factor dot value equals true. That's the prime factors. Select factor dot key, which is the number. So this is a link statement. If you're not familiar with link, what I'm doing here, it looks a lot like a SQL statement, and it really is. It's just that it kind of reverses how things work. It says, okay, first of all, where is it coming from? So right up front, you know where the data is coming from, which I kind of wish SQL statements were this way. You have to say select star from, and then put the table and go back and say, here's the columns. In this case, we're doing the opposite way. We're saying from this factors list, let's name each one, each row, we're going to name factor, kind of like a for each does. And then we can use that factor to then say, okay, in that row, factor dot value. Remember the key in the value. So the value is that nullable Boolean. If it's true, that means it's a prime number. So we're only going to select this where clause filters to say only the ones where they're prime. That's true. Then we get to select which fields we want to return, or we can return the entire factor. In this case, I just want the keys. Therefore, factor.key. So it's just going to return an IEnumerable list of IEnumerable of type int. That's going to be my entire list. And the cool thing is that I can then say console write line, the largest prime factor is, I can say prime factors max. There we go. So the largest prime factor is that one. And then I can say, here are all of the prime factors. And I'll put a console write line in between these two. And then at the end, I'm going to do a for each. And I'm going to say for each int factor in prime factors. Whoops. There we go. So for each factor in prime factors, I'm just going to print it out. And that should take care of all the requirements we have. So let's just kind of review what we did. We first just said, okay, if the factor count is 0, that means it's a prime number. Therefore, it's prime. But if it's not 0, then we're going to say, okay, that number is a composite number. We grab the factors, the whole list of the dictionary, we count them up and say there's that many factors. That's the overall factor count, not just the prime ones. So there's many factors in this. Then we pulled out all the keys where they were prime and put that into a list. And we said the largest prime factor is, and said max. Now, most likely, since we're not doing any kind of ordering anywhere else, we could actually say the last one, because we always count up. So 2, 3, 4, 5, 6. And that's how we add them into the dictionary. So in theory, the maximum one would be, and also the dictionary should order it, I believe, by the first value, the key. But in any event, it should be the last one. However, this just makes doubly sure of that by saying the max. It's going to find the maximum integer in this list. So the largest prime factor is, and it gives that number. I'm going to put a space and say, here's all the prime factors. Now, of course, it doesn't include 1 or the number itself. That's okay. That's part of our assumption. And then we loop through all of those ints and just write out the factor. Let's see how this works. Now, I'm pretty sure I have a bug in here, but we're going to find out real quick. Prime number, let's say 18. And yep, there's the bug. So the bug is, and you may have noticed this, and you may have been yelling at your screen, that's cool. I do this a lot. I forget about it, or I'm not always sure which ones cause problems, which ones don't. But in this case, invalid operation exception. Collection was modified. Enumeration operation may not execute, which is kind of funny. May not execute. You stop my program, so we won't know. So what it's saying here is you can't modify a dictionary if you're looping through it in a for each, or a for that matter. And so the reason why is because a dictionary, if you modify something, you may be causing it to change its position. And that's what we're looping upon. And dictionary is a little bit, like I said, harder to work with than a list because it doesn't have all the nice bells and whistles. In this case, it's kind of biting us. But don't worry, there's actually a quite easy fix for this. And that is, we can say dot keys to list. So this is now a list of int, not a list of key value pairs. And this is the factor. Okay, this is the key that we're checking, which is a factor. But we don't have to say factor.key anymore. We're going to say factor because it's going to be an int. So it's just a list of keys. We can now do this. And there we go. So we're actually creating a new list that is all of our keys to check. And we're checking that key to see if, or that factor, to see if it is prime or not. If it is, then we say output, which is our dictionary, and this factor set to true. We're still modifying our dictionary every time, but we're not looping over our dictionary anymore. We're looping over the list of the keys, which actually makes a copy. It's not the same, it's not the dictionary anymore we're looping over. And that should solve our problem, but we'll see. Okay, check for prime. 18. 18 is a composite number. There are 3 factors in 18. The largest prime factor is 3. Here's all the factors, or prime factors, 2 and 3. Okay? Now, there's more factors than that because we also have 6. Now, there's also one more. And this is why you always do something you can test. So there's 2. So 18 divided by 2 is 9. And that should give you a hint right there. 18 divided by 3 is 6. So you can't divide 4, 5. We already did 6. So that's the next factor. But then we also have 9. And 9 is not in this list because it says there's only 3 factors when there should be 4. 2, 3, 6, and 9. So where's our problem? Well, it's in our efficiency right here. Less than or equal to max, which is divide by 2. Or less than max. Let's do less than or equal to max. And check this out again. 18. There's 4 factors in 18. The largest prime factor is 3. So now that solved our problem for us for numbers that divide by 2 evenly. For every other number, we're fine, but we had to make sure we went all the way up to the middle, not just one below the middle, which before worked just fine for finding out if it's a prime number or not, but it didn't when we're trying to get the factors because we have to take into account that divide by 2 factor, which in this case was 9. Okay? So now I can throw large numbers at it. Let's do like so. And wow, there you go. Again, now it's random, but that's a prime number. Let's try one more. 1, 2, 4, 5, 8, 6. Let's do 7 instead of 3. There's 14 factors in that number. The largest prime factor is 1447. That's pretty impressive. And notice how fast that is. That's a very fast prime number calculator. Now, the one thing to note is that we're limited right now by the size of an integer. If we wanted to go any further, I'm going to hit no here. If we want to go any further, we're going to have to change everywhere we say int to say long instead. So you have to modify that in quite a few places. So anywhere we're saying int, like here, and here, and here, and here, and here, and all these spots would have to be long instead. Now, are you going to run into this? Probably not. Let's just take the largest possible int. 2, 1, 4, 7, 4, 8, 64648. I'm sorry, 647. That's the largest number you can calculate. It's just over 2 billion. And it's going to take a bit to calculate this, but it's actually a prime number. So, yes, that's a very large number. If you're going to calculate more than 2 billion, then you need to move to a long, which that's a very, very big number. Okay. But your computer might not be able to handle much larger. But even that wasn't that long to calculate. And we're calculating a 2 billion number prime. And we calculated it all the way up through. We didn't just say, just tell it's a prime or not. We actually went all the way up and did calculations for every single step. So do you want to do long? Probably not, but just know it's there. Okay. So that's the challenge. That's the solution. I think we covered all of our bases. We, ran into a few things where we have to use some more, like I said, edge case stuff, like using an actual link statement, not the shortcut for link, like link or m.where or something like that. So we actually did a more link statement. We dealt with dictionary and the nullable Boolean. And again, I didn't have to use nullable Boolean. I could have used a bool and set things to false, but I don't like values that can be misinterpreted as real values. So I wanted to have that null so that we never got a value back and checked it and thought it was a real value. It's actually just not set yet. Okay. So the dictionary, we played around with that. We played around with how to, worry about the for each when we're making modifications and all the rest. So hopefully you learned something from this, and hopefully you got something similar, probably a little different, but at the same time, the output hopefully was similar to mine. Okay. Thanks for watching.